My name is Dietmar Kühl. I plan to talk about quicker sorting, which is actually about quicksort, which hopefully everybody knows, but I'm not really talking about quicksort. Well, I do, except that I don't. The reason I like that talk is it is basically representative of the work I'm doing without actually talking about anything I do in my work. I work at Bloomberg in real-time data distribution, which basically is intended to process lots of data and distribute them quickly. And we actually have to pay a lot of attention to even small details because otherwise our software is not fast enough. And traders generally do not like that. So this quicker sorting stuff is about basically, here's quicksort, now let's make it actually fast. I may not be entirely everything accurate, so I may be lying, I try not to. This is just saying you cannot sue me or the company. So what I'm going to talk about is quicksort on quicksort. I guess everybody remembers how quicksort works. I'll still quickly go over it. And then I basically start implementing quicksort and measuring how fast it is and tweaking it, measuring, tweaking, and so on. And eventually towards the end, if we get to that, I will quickly run over what it takes to turn the quicksort, which I've implemented, into a generic version, although I don't yet use the simpler original version rather than the full-blown, because it would just not fit on slides. So, before starting, I will compare my implementation against standard library implementations, and also clarify that actually the standard library has a number of sorting algorithms, and the main reason they do have different sorting algorithms is they have different performance characteristics. And although the differences are small, they actually end up doing mattering. So standard basically has three approaches to sort. There's stood sort, which effectively, as far as I know, everybody implements as a version of quicksort, which is pretty much along the lines of what I'm doing over here. Also, I want to be very clear, none of the ideas I'm presenting over here are my own. I actually stole all of that from people who implemented any of the standard library implementations. So I had to look at Clang and libs stood C++ to figure out what's going on in there. So the intention of all the algorithms is that they are n log n, which is what you would expect. Even sort, which is in principle quicksort, which everybody knows is not really n log n, but the standard has required them to be n log n, so actually quicksort, vanilla quicksort is not a valid implementation. And they're not implemented that way. But sort is basically typically based on quicksort. Stable sort typically is not. The difference between between sort and stable sort is just the stability of elements. And just keeping the stability of elements, it would be really nice if we could keep that and still be fast, but it still takes some time. And then there is another version, which is heap sort, which is meant to be reasonably fast and in memory. But I will also show what the performance characteristics of these are quickly. So, when talking about performance, it always matters what are we actually looking at. The sequences I'm comparing are all random generated, so they're not really real sequences. However, just random generating, let's say, a sequence of integers is entirely pointless because that is not representative of any real data set. It's way more reasonable to claim, I don't know what my computer is doing here, it's way more reasonable to claim that the sequences are actually have sets of overlaps. That is, they will contain various degrees of overlapping data, which is quite typical. Like, if you sort names in English names, there are lots of Smiths. So you sort along those, and actually, the equal ranges are one of the things which quicksort actually does struggle with. So the data set basically contains multiple variations of random things with various numbers like overlap, like most things overlapping to roughly non-overlapping, as well as an ascending, descending, and then one sequence which is all the same. The performance graphs I'm showing will all look like that. They're all scaled. They're normalized on stood sort. because my assumption is, well, stood sort, this is what we want to beat, or this is what the benchmark is. So stood sort, this is roughly a log scale a graph over here. Stood sort is meant to be the most efficient one. The stable sort, over here you can see, is mostly something like, well, maybe 10 to 20% slower, but that already is sufficient to matter. If you do a lot of these things, you would prefer to go down. This up here is heap sort, which basically says, yeah, don't use it. Heap sort, it doesn't really help you much. It's slower, it is not stable. So, quicksort. Everybody remembers how quicksort works. It's really simple, just a few steps. We get an input, we choose a pivot, doesn't really matter what that one is. And then we basically classify all the elements into bigger or smaller. So basically we say the blue one is meant to be well, less or equal. This is a condition over here. And if that is true, I paint it green, otherwise it's red. That's just an example. And then the next step is we partition these things. Partition is just using that predicate to sort these apart. And then all quicksort does is, well, we recurse on the two subsequences. One important part over here on quicksort is actually that the partition point, we know that the partition element is in the right location, so we can actually take that one out. The reason that is important, if you do not take that one out, your algorithm will not terminate on if you have equal elements. However, taking that one element out, you definitely make progress. Even if the blue is on either side, you always have one element less. Implementing that, that's really straightforward. Everybody can do that. I'm just using a standard library algorithm over here, going, all right, well, if the length is just one element, I pick a pivot. For convenience, I pick the pivot right at the end of the sequence, because that's the easiest one to use. We could then just go partition begin and end, which is what's happening over here. It's comparing against a pivot. Unfortunately, you cannot see the red thing, but it basically says in red pivot. Once I've done that, I just swap the partition. I hope everybody knows how partition works. It yields the partition point where the sequence starts to be false rather than true. That's the element which the pointer which is returned over here. So all I need to do is, because the pivot is in that position, I just swap these guys and done. So this quicksort, that should be quick, right? So comparing that, it turns out that I couldn't be bothered to wait until it has the full range, because it just goes off scale. This is a really bad implementation. Of course, everybody from uni knows, yes, we need to choose the pivot carefully. And popular choices for professors is we choose the median of 3. We just take 3 elements, for example, the begin, the last, and the middle. We could choose any 3, it doesn't really matter. We work out which one is the best one, and that should actually solve some of that problem. That's a little bit extra cost to determine the median, but certainly always using the last one is supposedly bad. In fact, it is bad if the sequence is entirely, I think, ascending. Then you basically, taking the last as a pivot, you basically chop off one element at a time, which is no good. So implementing that just amounts to a very small change. Instead of choosing a pivot, the pivot is chosen out of 3 elements, and there's a small sort, which is not particularly interesting, but I will show it anyway, which basically, given 3 pointers, puts the pointer, the element which should be used as a comparison, into the middle element, because that's kind of the median. So this is how that would be implemented, and all that is this kind of the minimal number of comparison operations you need to do for sorting 3 elements. Sorting 3 elements is borderline annoying, because you cannot just, there's no nice divide and conquer or something, and you just type it out, and it just does the right stuff. There's nothing, no trick in here at all. Using that hopefully improves things, and lo and behold, it does. The curve, however, still looks the same, right? I hope everybody understands what is going on over here, right? We basically picked out the pivot, but actually it doesn't really help us. The reason that doesn't really help us is primarily actually all the cases where the median of 3 still produces a bad result. Now you go, well, that should be unlikely, isn't it? Except no, it's not. The pivot of 3 elements, or the medium of 3 elements, if all 3 elements happen to be the same, is actually the one element. And then the partition does not make much progress. It only progresses in one element. You could go and say, well, I know what to do there. We can do what is called a fat partition, where you basically partition instead of into 2 sequences, actually into 3 sequences, where the first element contains all the elements which are bigger, the other one contains all the elements which are smaller, and then the middle section which contains all the elements which are the same. Unfortunately, in practice that doesn't work that well. There's a different trick which actually works much, much better. And the idea over there is something which goes under the name of intro sort. Intro sort is really just this very simple facilitation on top of heap sort. The idea of intro sort is, instead of actually just using quicksort naively, we basically observe how often we have invoked the quicksort already. And if we feel we have invoked it too often, we stop doing that and rather use a different sorting algorithm which hopefully works better. In fact, you could use something just like heap sort. Although heap sort was bad, once you have a reasonably slow, small sequence on which we suspect that quicksort is no good, heap sort is actually quite reasonable. So the idea is just monitor. If you have, say, we determine the logarithm of n of our original sequence, and if we have done more than 2 log n recursive calls, we decide, yeah, that's too low. The 2 log n is basically a value which comes out of analysis. You can try to figure out what works best, but basically it's a random number in the right ballpark. So how is that implemented? The basic idea is just we, instead of calling our sort, we basically have a depth check on top of the sort. If the depth is too deep, we basically call, over here the code actually uses stable sort, because that came out slightly faster. It doesn't really matter whether you use stable sort or heap sort. Effectively, they're not that interesting. The only question is how to come up with the max, and for the benchmarks, I use the very naive version where I basically just determined the size. And then over here, this is basically just counting how often I need to shift before I have no 1 bits, which is really massively naive. Unfortunately, I see that, oh, I know, this actually uses an int. In practice, you wouldn't use an int, but if I tried to use an unsigned int, it wouldn't have fit on the slides. So in practice, you obviously use unsigned int over here, because otherwise, if you have a sequence which actually needs 1 set bit, this loop would never terminate, because it always shifts in the top bit. Okay, so using that, we get a nice graph which actually already brings us down to a substantially faster thing to go. We went from going all the way off to basically staying in the ballpark of what stable sort does. We obviously don't want to do that still, because stable sort would be, we would just use stable sort because that is giving us better results. We want to bring it further down, ideally below the blue line. So what kind of ideas could we have instead? And this is where something odd comes in, and we all know that insertion sort is really bad. Right? Insertion sort, if you run it, it basically is a quadratic algorithm right from the start on all n. However, if you actually make the math and compute how many operations does it do, if the number n you have is actually reasonably small, something like 20, 24, 30, something in that area, if you make that computation, you find that actually it does not do that many more or even less operations than a partition would do, because a partition would go through all the elements roughly the same and do some other operations. So the idea over here is to say, well, yeah, but anyway. The idea over here is to say, let's do something different. Basically, once we know our subranges are small enough, we stop doing heap sort. That is possibly not a good idea to quicksort, to continue doing quicksort, but rather let's just do insertion sort. And there are two variations of insertion sort which you could do. One is to say, all right, we just get the sequence and we just sort that instead of the recursive call. And another variation is we just stop sorting and eventually use insertion sort on the big sequence. The basic idea of using it on the big sequence is elements cannot move very far, and the cost in insertion sort is how far elements actually do move, right? You basically go and find the place, but you already know that the elements will not move outside the bracket of the size you have produced. So even though you use it on a huge thing, and conceptually the call would be really expensive, because the elements only move locally, it should be okay. And in fact, it kind of is okay. I'm only showing one of the two variations, the one which is easier. That is basically, well, actually it doesn't really matter. This is the one which is embedded, and unfortunately you really do not see the red stuff over here. The basic idea of insertion sort is we just, well, if begin and end are the same, then we don't do anything. Otherwise, we basically iterate over each element and just see whether we need to exchange this with the previous one. And, well, unless we are at the end. And if so, all we do is we basically lift it up into a temporary variable, move it over, and then keep shifting the things over into the empty slot until we found the place where it needs to be dropped. Then finally we just drop it, and so this is the moving out bit, this is just the dropping bit, and this is all we need to do. This algorithm is embedded into basically doing the small section. You can just hoist it out and do the big part as well. It's essentially the same algorithm, just called in a different place. And this graph actually shows both implementations. You don't really see much of a difference. The orange and yellow line over here, which basically are just the same. So the idea that people say, well, we have just touched the memory and it should be good, and it should be all hot in cache, over the big insertion sort where people say, well, we have all the insertion sort code hot and we use that, kind of that indeed keeps its balance. It doesn't matter whether you use one or the other. One thing which I hadn't mentioned actually on one of the on the previous slide over here is this line actually also contains two lines, which is interesting, and the two lines is the yellow line on top, which you actually see is computing the median, and the orange line essentially under the top is just taking the middle element. So actually it doesn't really matter whether you compute the median. It is more important to actually take something in the middle in case something is sorted. Okay, so far this is relatively simple stuff. Let's do something which is not as obvious to be sensible and talk about the recursion. So in quicksort, we actually have two recursion branches. So we cannot really use tail recursion. However, tail recursion is actually something which is really nice to use, because if you use tail recursion, you don't really recurse, you don't really build up a stack. Building up a stack is conceptually actually reasonably cheap, but maybe it's slightly cheaper not to do so. And the basic idea over here is to say actually instead of having the compiler try to figure anything out, we just pretend and put one of these two branches into a loop. And the basic idea is we know that on a smaller sequence, we cannot really branch as deep as we can possibly branch into a longer sequence. So if we have one sequence which is really long after the partition, we basically just use that, and instead of recursing into that, use that in a loop. And the other one, we still have to do the recursion thing, otherwise we would need to maintain a stack, and that becomes really annoying. So that's not going to happen, but basically using a loop for one side but not the other is a reasonable idea. And it's actually also not very hard to implement. All we need to do over here is to go, well, before we recurse, once we have determined the midpoint, we just see whether the mid minus begin, so that is the first range, is smaller than the second range. If so, we recurse into the smaller range and just adjust things such that the next setup is of the loop, which we already have essentially, does the right thing. And If that condition doesn't hold, we just do the opposite. We recurse into the second sequence and set things up locally to basically become a loop. I think the main change over there is there's another change which is not in here, but basically instead of having an if on the top, it is just a while loop. And that doesn't make a huge difference, but it makes a small difference. And by now we actually kind of already in the area of sort. So basically we try to just bring it down slightly further. So basically what you can see over here is the yellow line is slightly above the green line, and the green line is basically the tail recursion approach. Okay. So a small win. Let's see what else we could do. The bread and butter algorithm over here of quicksort I haven't even touched yet, and that is partition. Now let's quickly talk about partition, because it's a simple algorithm, and all it does is and see whether we can do that better. The idea of partition is basically you give it a range, begin and end, and a predicate. It's a binary predicate, and it sorts all the guys for which the predicate yields true to the front and everything else to the back. That algorithm, I would claim its main application is in sorting things, whether it is nth element or sort. Partition is a workhorse underneath, but it's actually also useful for other things, where basically have objects and you need to just partition them. You're not interested in the order, you just I need to all those elements over here and all the other elements over there, which actually in sequential programs is maybe not that often useful, but in parallel algorithms I found that it's actually fairly common to actually sort things in one direction and possibly do entirely different things afterwards. Okay, so partition. How does partition work actually? Let's just start with the example of where we just said, all right, here we swap things over. The way partition works is we start off with a pivot element over here. The first step is basically putting the pivot element out of harm's way. So it basically always goes either to the end or to the front. And it will actually later be important to actually put it at the end. Well, or it's important to put it in one of the two sides because it can actually be used for interesting things. So the next step is to basically set up two pointers or iterators, one pointing to the first element, one pointing to the last element. And then we find basically from either side the first element respectively which needs to be swapped, which is in the wrong location. So over here in the first iteration there's just this red element and the green element. The green element needs to go to the first half of the thing, the red to the second half. So we find these guys and we swap them. And once we have done that, we find the next ones, swap them, find the next ones, swap them, and so on. And eventually we have all of them partitioned. The last thing we do is we stick the, well, this is actually part of the sort algorithm, to stick the partition element back into the partition location, and we are done. So that's partition. Implementation of that is exactly just what I said. There's nothing particularly interesting in here. I choose not to use find. Effectively, this algorithm over here is find, which is basically finding over the sequence and that predicate, and just incrementing that. The red stuff, which is basically unreadable, is a slightly compressed version thereof, which is basically doing a find on reverse iterators. The reason it's slightly compressed is the pre-decrement does just the right thing. We are basically off the end. We know we have at least one element, is what we just checked before, and we can move that element forward before checking. In the other case, there's a slight dependency, so it makes it slightly neater. This is all the partition does. Now, using that partition versus standard partition actually doesn't make much of a difference. The green and yellow line are just the same. So pretty much the standard partition probably does just that. However, maybe we can do actually less work. So one thing you may have observed is that all the inner loops make two checks. They check, is the element, is the iterator at the end? And if it's not at the end, does it need to be moved? Maybe we can just fold these two conditions into one. And this is basically the idea of a sentinel. If you have something which we know we will find, we don't need to check whether we run off the end, because we will find something anyway. And if you basically put something into the back which says we are looking for an element which is not less than the partition element, this guy will be exactly one of those. So we can actually leverage one check out. This is the idea over here. Instead of using that, we just basically, because we know how our pivot is structured, we can just drop that. So we can do that. There's an interesting thing over here. Did anybody notice what I just did to the sequence? Under which conditions that may be a very, very bad idea? Empty? Well, we actually checked that. That's fine. But there's a different condition under which that is a really bad idea. And that is this code with a check in actually always terminates. It even terminates if the less than operator is not really a strict weak order. It turns out that although sort and partition would over here actually require that the less than operator is a strict weak order, sort certainly requires a strict weak order, people get upset if their code all of a sudden crashes. And I know for a fact that the reason GCC actually does that check is if they remove it, client software crashes. And instead of crashing, people just get are apparently okay to get a non-sorted sequence. But this is actually something we're basically giving clients a non-optimized version, which actually is kind of friendly to operations. It actually causes problems later on because you cannot improve the performance. Clients have started to rely on kind of broken behavior. So when I say later that I may have reached a more efficient implementation than libstdc++, that is partly down to them having not made this optimization. So basically removing the check for end is basically, if the less than operation is really a strict weak order, it's a perfectly safe thing to do. If it is not a strict weak order, this code with a check actually still terminates because it always scuffs something off. In the other case, it may actually just walk off the end and basically cause software to crash. Okay, so on that end, that was really simple. On the other end, we unfortunately do not know anything about the first element at all. So the idea would be to, or the idea of in that direction is, so that we can also get rid of the second comparison, is to actually, in the first iteration, find something which is of the right shape and put that into the correct location, and then basically always use the Sentinel implementation. So this is basically, this is the original code. So we basically first need to prepend that with something which finds the first element where things go wrong, so it needs a special first loop, and from then on we just carry on using the partition, the Sentinel version. And it actually does again make a difference. If you see the green line is basically straddling the blue line, the yellow line pretty much stays below the blue line, so we actually have arrived at something which makes the quicksort more effective than studsort. When I say studsort over here, this is the studsort at some point in the past used by libstdc++. The behavior of libc++, which I compared against as well, is similar but slightly different. They do quite a little bit better. Okay, but we're still not done. We still can do better. And one of the things is, if you actually have a really small sequence, it may be reasonable to, instead of doing an algorithm which can deal with longer sequence, deal with a really small sequence up front. The idea over here is actually really simple and straightforward, and that is, if we know the length of our sequence, if we have 0 or 1 element, we know we don't need to do anything. That's great. If you have only 2 elements, the worst thing which could happen is that we may need to swap them. So we can special case that. You already have seen the sort for 3 elements, which was a little bit convoluted, and from then on they start getting more and more convoluted. I found that doing it for 4 elements as well still gives a little bit of payoff. For 5 or 6 elements, although I coded them out and it becomes really, really annoying and no fun, it turns out that it starts getting worse. So you basically, seems to be local optimum with sorting 4 elements, which is just the logic on the screen. It doesn't do anything fancy. It basically does a 3-element sort and then finds the location. This is pretty much like a hand-coded version of the insertion sort, which is tailored for a sequence of 3 elements. And the result over here is, if you look at it, ends up being roughly the same. The reason I think I still kept it is I did actually all the combinations and try to find the one which is overall the best, and keeping that one in actually does improve things. Okay, so there's another thing, and this is basically, I had in the beginning mentioned that if I have an equal sequence, these actually do happen in practice, and maybe it is good to detect them. And the basic idea is actually, instead of having a fat partition which does a big and basically separates things into 3 sequences, rather do something which is a lot cheaper, and basically instead of partitioning into 3 sections, do partition into 2 sections, but observe how often things were actually swapped. Because actually, if you have a partition point which is all the way bigger or all the way smaller, then the partition actually didn't do anything. It would not swap any element. So at that point, you basically get for free an indication whether something may have happened or not. And the basic idea is to say, right, if the partition didn't do anything, we may not have hit a really good thing, so it may not be sorted, so we still need to deal on that. But we can basically just have a counter. If that counter is which counts the number of swaps. If the number of swaps is 0, we just gamble on saying this thing is nearly sorted, and we do basically something like an insertion sort, which stops if it starts to do too much work. So this is basically the entire idea. The partition, I didn't implement that over here. The partition really just, every time it swaps, it basically keeps the count swaps up to date. So basically, the count, if that is 0, we do an incomplete insertion sort of the front and an complete insertion sort of the end. That is slightly more interesting, and that is basically still the same insertion sort, except that basically it counts over here its own counter, and if that has reached the limit, where the limit is something like in the order of 768, somewhere in there, it seems to be the best, then it just stops. And it can easily stop over here in the first case. There's nothing to do. In the second, because we basically just found that this element is in the wrong location before doing anything with the element. It's a little bit more annoying and complicated if we find inside the move, where we basically have moved out an element and start moving it forward. If we find in there that the count is bad, we still need to put the moved up element back into the slot, and then basically return false in both cases to indicate the insertion sort didn't finish sorting. And otherwise, if that thing actually finished sorting, we return true. And this gives us this nice graph. This makes actually a really large impact. So this is basically the idea to instead of doing a fat insertion sort, separating equal sequences into 3 sections, to say we detect the more or less equal sequences directly. If you do not do the insertion sort thingy and only detect that the partition didn't do anything, it doesn't do as well. There's basically, it seems if things are slightly unsorted, this still picks up things quite nicely. Okay. So this actually gives me an implementation of quick sort effectively, which is better than the standard library compared against, which is libstdc++. And I do know that they basically could do better than they currently do if they basically did the partition thing. Is that something which should worry us? Okay, no, it should not. Okay, cool. Would be kind of awkward to talk over that. So, all right. So this is basically the result. Now, compared to the original implementation, this is all the implementation. You cannot read that. I cannot read that either. It's just qualitatively. You can get a color version of that, which basically says this is the small insertion sort. This basically dealing with small ranges, including the small sort and the insertion sort. The white part is the main sort algorithm. The green part over here is the partition, and over here is basically the blue stuff is what is that? That is another part of the small sequence stuff, and then there's some red stuff at the bottom, which is a driver. Now there's a lot more than the original implementation, which was just that. So although quicksort is really simple, this is quicksort. Once you have implemented it all and basically made it really effective, this is what it becomes. A real implementation probably wouldn't do it just in one function, which would just basically split the thing off into something like a dozen smaller functions and would be roughly twice as much code. The performance of doing it in small inline functions versus that is does not make much of a difference. I don't think it makes actually effectively any difference. So I didn't have any measurable difference. In any case, this is the original version, the other one is the full-blown version. And for other algorithms which are kind of non-trivial, you have similar situations that actually real implementations can be quite a bit more complicated than a simple one. All right, so before finishing off, because there's still a little bit of time, I had originally produced that for students, but I found that quite a number of C++ developers are afraid of templates. Who writes template on a regular basis? So a couple of guys. Who has never written a template? Okay, everybody has at least written a template a little bit. So I just want to use the original sort to quickly show that actually it is non-scary to create a template version of an algorithm once you have an implementation. And that is basically, this implementation was really bad. It is just specific for one type, and is actually, so it's only sorts integers, and moreover it only sorts integers in a built-in array. So, well, the built-in array could be a vector and you get the integers, but actually it could be made much nicer. The simple stuff to make it applicable for all types is all we do is we hoist out the type. We just say type name t, and every time we use integer, we just move that out. Everybody can do that, so I don't think there's an excuse for not doing that for things which are of general nature. It becomes a little bit more nicer still to basically, instead of moving out the type, actually moving out the iterator, which still makes things quite reasonable. No, instead of using pointers, we use iterator. There's one change which is substantial, and this is the one over here, where basically decided I use the C++14 feature to gloss over that, and that is the lambda, you need to specify the value type. If you stick in the iterator, you don't really get the value type out directly. We can get the value type out even without C++14. C++14 makes it nice and easy by basically just using a forwarding reference over here. That's the auto-ref. Otherwise, we would have needed to write something like type name, iterator type, traits of iterator of value. Yes?
What's the advantage rather than doing like a cross-reference there? Like why also use...
Okay, so the question is, why don't I use auto-constref, but rather auto-ref? At least this is how I understood the question. And the answer is, actually, this guy works even if your comparison operation takes non-const references. It deduces the type correctly. It will in all cases be a reference. It will either be a const reference or a non-const reference, but basically using auto-ref instead of auto-constref makes it slightly more general. So it's not a big deal. Most comparison operations are meant to be to work on const values, but using that notation doesn't require that. Okay, and then after that there's one remaining bit, and that is at the moment the code just uses less than operation. You may want to sort your elements the other way around, and there's a simple way around that, and you basically do type name comp, and And all you do is instead of, you take a comparison object as an extra parameter and use that. With, I think that is a C++14 feature. I could have actually made the comparison and the comparison template argument a default. So basically writing on the top line type name comp equals std less of bigger and smaller, well, greater than less than, and then on the next line comp c equals comp would basically have conflated the default implementation together with that one, which is a nice, interesting thing. So that on the quicksort, just for kicks, in case you want to try things out, whether you get a good or reasonable, good or bad quicksort, and that is there's actually an approach to kill quicksorts. The idea is you can basically, the moment you can have a parameterizable comparison operator, you can give the quicksort a comparison operator which actually determines on the fly an order which is bad to the sort. Right? Nobody would use that in real production code. This is more or less to check whether your quicksort is prone, or the sorting algorithm is prone to doing something bad. So the idea is every time something is compared, this quicksort killer basically determines the minimal amount of order it has to do. It basically goes, yeah, okay, I say this one is not smaller, bigger than that one. And if I compare something which is compared again, then I have assigned some order for those, but otherwise I delay that until later. The entire logic of that operator is basically that, which basically assumes we have somewhere and probably a hash map or an array, depending on what kind of elements you get, of values where you can basically store an integer associated with a value. Over there it's just using integers, so it could be an array. And every time it does something, it basically looks at the array and says, all right, is the element initialized to max, which is basically the indicator that we haven't given this thing an order yet. So if there's no order given yet, then we basically assign the order randomly by basically keeping some kind of candidate around. The reason for the candidate is by keeping that around, you can make it slightly more hostile and basically go, right, if you don't know whether X or Y is how they're ordered yet, we make up an order and we define that whatever comes out of that is the one which is, this our count is basically giving the next order. If either one of these things is not set, we basically just compare the, so if this would give the order of one of the two elements and the other one would still stay with max. If we have already both, we don't do any of that and we basically know what order these are. So this thing would produce a consistent order. What order that is depends on what arguments are fed to quicksort. And this is basically a way to discover whether your quicksort tries to cheat and just tries to come up with a good pivot, because the pivot wouldn't help over here. It will always produce a sequence of elements which, depending on how many elements the quicksort uses to sort, has only these elements sorted and everybody else compares on one side of the quicksort, and you would need to recurse into that. So that's on that. Okay, this is just colored versions. There often something isn't quite working. Why is that not working? Okay, but I think this is my last slide anyway. You see that funny ball over there? Something confused my computer. Okay, so the last slide really is about questions. Anybody having any questions about any of that stuff? Yes. Yeah.
Is just one thing about the optimization of the partitioning when you just removed the comparison between the iterators. It's based on the fact that the less is a strict operator, but when once you use a general comparator, you would have a defined undefined behavior if the comparator is not strict.
Yes.
Probably, maybe you just think about it. I think you could use a context expert overload to check whatever the comparator returns true for the same value for a value compares against the same.
Okay, so the answer to that is actually we don't need to faff about in the sort in any shape or form, because the sort algorithm always has a requirement that the comparison argument, whether it's less than or any other comparator, provides a strict weak order. We could have chosen to not use a strict weak order, only use the weak order. Something similar, the sentinel would actually go onto the other side to do the same comparison, but you could do the same thing with a strict order, with a non-strict weak order. The main issue which happens with typical user applications when users stick in a comparison or a type for which the comparator is not a strict weak order is not so much that it's not a strict weak order, but basically an example is sorting doubles. And so, and the comparison operator, the lesson operator on doubles is not necessarily a strict weak order, right? You can safely sort doubles in using std sort. There's no worry, under the proviso that none of your doubles happens to be a none. If there's one none in there, then this blows away the strict the property that all the elements have to satisfy strict weak order, or the comparison defines a strict weak order on all the elements. So this is essentially the real world problem is nonce and floating points. They just sort in the wrong way. It's not about the strictness or the non-strictness. Yes.
For your optimizations, do you need to define some thresholds?
Yes.
Are you confident that these constant thresholds are not dependent on specific architecture you're running on, meaning a specific CPU with a specific frequency and cache line and memory or whatever?
Okay, so I will abbreviate the question slightly. So the question he had is, I had to find a number of constants, whether it is when to stop quicksort and go to small sort, or how many elements I do before stopping any of that. I have tried them with the same set of values. I actually had to, the way I set this stuff up is basically I had a big array of what combinations I want to test, and I tested them in all kind of variational combinations, which took quite a while, and then basically just sorted out the best ones. And it's basically the typical curve of where things work flattens out quite a bit, and so they're basically bad. At some point there's a local minimum, which element, whether you go, let's say, the one end maybe 16, the other end maybe 24, which element you use in between doesn't really matter much. And I found similar versions applied to different architectures. So the architectures I've used were all Intel architectures, but one was basically a laptop, the other one was an iMac. This is what I had available at the time. I'm reasonably confident that you can find reasonable constants which work reasonably well across a broad set of actually problems. The entire advantage of these things actually quickly goes away depending on when your elements are actually bigger. Like if you actually, let's say, sort reasonably sized chunks which you move around, then the advantage of the optimization quickly diminishes. It's basically something which works only with on a relatively small set, or it makes a difference on a relatively constrained set of sizes. But all in all, I think you can come up with reasonably good constants which work well on cross platforms. Obviously, the next step is the standard library is meant to actually find these correct constants for all correct implementations. And to a large extent, one of the things I'm interested in personally is establishing things to figure out what works well on which architecture. Because there are actually algorithms, like sort is not one of those, but there are algorithms where one algorithm works very well on one architecture, but a different, on a different architecture it does not work well at all. And so you actually want to pick what you use depending on the architecture. So if you're really interested in performance, I think you need to profile on the architecture you're really targeting. You can get a reasonably good version based on general approaches, but eventually you need to test on the hardware you're targeting. I hope that answered your question. Anything else?
Yes, I have a similar question to the last one, but not related to the architecture, but related to the data itself. Are the considerations we made and the results we end up with dependent on maybe the distribution of data and properties of the data set?
Well, generally when you do benchmarks, the benchmarks end up being optimized for the data set, sort of. I try to make the data set such that it actually is reasonably representative, and I also basically choose the algorithms and basically generated different data sets on each iteration where I tested things. So between iterations there were different data sets. They had still the same property of being random generated rather than finding large enough data sets, real world data sets which were sorted. So I have a reasonably high confidence that they would apply to other things as long as they do have overlap, for example. If they don't have overlap, most of these things don't really matter because actually there's no need to do a pivot. If things are really strongly random, then a lot of these things don't matter at all. But I think I try to do something which is representative of the data sets. And the way to test that again is if you want to know which algorithm works best for your kind of data sets, you use these data sets and you benchmark on the data sets. I think if you really target good performance, you need to test, well, on the correct platform, on the correct data sets, and not on random data. That's for sure.
Thank you for your talk. Actually, if I well understood, you got a 10% improvement of the performance with comparison with standard store. But the cost is that you don't use the algorithm that is well tested and it is everywhere. So what do you think it's the threshold of improvement you would say the algorithm I wrote is approved? Because, yeah, so.
Okay, so I concretely know because I do talk to people who do implement the standard library, like Marshall Clow or STL or some of these people, and the answer is relatively simple, right? They go, well, first of all, the implementation typically is good enough. Why bother? Why break it? A 10% increase may seem a lot, and actually I'm interested in that. If you really want it, you want it. On the other hand, changing stood sort with some of these changes will break some users' code. And the standard library implementers are actually very, very worried about breaking users' code. So the threshold before actually replacing any of the standard library implementations code is fairly high. You could go, well, but if you port that to a different platform, that code might break over there anyway. And the answer to that is yes. And that is actually kind of in the interest of the respective standard library developers. They're interested of everybody being able to onboard their implementation, but once there, they have an interest that people stay there. So I think that the way to go over in that respect is to actually say, all right, I use the standard library algorithms until I find that a different algorithm with a similar interface is a better one, and then I may use that specifically, and hopefully there's a library of that. And similar to what other people say is I encourage everybody to actually create algorithms and benchmark them and make good algorithms and make them available somewhere so that people can choose and pick the algorithms as appropriate. Okay, I think we are pretty much out of time anyway, so thank you very much.